As the next speaker, we have Gaël from MIT, and yeah, he's been working with like Echo joint models, MIT GCM for quite a while, and yeah, one of the few, I think one of the earliest persons I've heard talking about Julia and how we can use that already many years ago. I think there was a JuliaCon presentation at some point.
2018.
Huh?
2018.
2018.
Yeah,
I remember that one. Amazing, exactly. And he's going to talk about ClimateModels.jl.
Cool, thank you. Yeah, thanks for having me. And sorry I wasn't here for some of the earlier talks. I had another presentation, which gave me an opportunity to advertise that one. So I presented two today. One is the Julia for Earth Observation workshop, which was this morning. There was a community effort. And then the digital twin for ocean robots project earlier today. And so these two sort of map into that. This is the model side, whereas the observation was first, and then the coupling was in between. So today I'm going to talk to you about the ClimateModels.jl package, which is essentially an interface to all of the best models as much as we can. So I'm going to be much more kind of inclusive in a way than taking the pure Julia road and sort of try to do something with models regardless of their language. So why do that? Why not just do everything in Julia? Well, I would argue that there's a lot of great and trusted models out there that we have no reason to exclude and that we should continue using. These models have large communities. They are not going to jump ship tomorrow either. So I see it as a kind of an inclusive effort to provide a general coupler or wrapper to models from Julia. And so one of the things I like, for example, is if you have MIT GCM on one side and then Oceananigans, which is sort of the port to Julia on the other, I want to be able to use both kind of equally with the same interface. And even with pure Julia models, I would argue that sometimes it's difficult to deal with everybody's choice of APIs and parameter sets and all of that. So what I'm providing with ClimateModels.jl is a kind of a smoothing over that and providing a unified interface. And finally, just my own motivation is, I want models that are written in Julia if I can, but ultimately I just want all of the models. And I want to be able to just run them with one click of a mouse. So these are the goals. Let me check my time, okay. Here is some of those models that I'm using with this and that I would refer as kind of trusted, widely used models. So the IPCC CMIP6 archive is one of them. This is a notebook that is a Pluto notebook where you can just select a model source and gets its output from the web, then start analyzing it. So there's a lot of those modeling efforts that have been built over time and are the state of the art today. Here is another, which I particularly like, the Hector simple climate model. So this is a fast, sort of low-dimensional representation of those big ones we just saw, or of what, say, the CLIMA model might become someday. And this is an image of, again, a Pluto notebook on the left and the type of things it generates on the right. The point of this partly is to show you that we can interact with all of the parameter sets for these models, regardless of their languages, through text files, which I'll talk about more in a minute. And the MIT GCM that's been mentioned before. So this is a differentiable ocean, sea ice, biology, atmosphere model that was indeed written in Fortran, has a large community of users, and nowadays with ClimateModels.jl and other packages called MIT GCM Tools.jl, you can essentially run any configuration of MIT GCM from Julia with just your simple interface. So that's all I'm going to say about those three. These are three examples of what's available within the suite of models within ClimateModels.jl. The original presentation for this package I gave a couple years ago in a very brief talk. And so you can find this one on the JuliaCon channel on YouTube. I'm not going to repeat that, what I said there, but I'm going to give you a couple of dates and then go deeper into a couple of aspects that I think are nice. Oops, sorry for that. So it's not into snow. So the model lineup since the 2021 presentation has increased a bit. So you'll see in there that some of the models we've talked about, Oceananigan, Zector, MIT GCM, IPCC, CMIP6, all of the stuff is in there. The left column is models that you run effectively, as in, you start them from a point or a parameter set and you compute. But on the right-hand side, there's also the other approach, which is the model has been run already, and all you need ultimately is to get the output and start your analysis from there. You can replay the models. And this is something that is commonly done for a lot of scientific analysis. So ClimateModels.jl supports both of those approaches. And as you see, I have examples, a bunch in Julia, C++, Python, Fortran, and then a bunch of file formats. The interface is this, essentially. There is a data structure called model config. Here, the very first block is how it works with a simple Julia function. So if your model is just a Julia function, all you end up doing is run model config, the name of that function. And the rest just runs for you. I'll break it down in a minute, but that's the idea of being able to run models with a click of a button, basically. What you see in the bottom part is the macro version of this. So same idea. What's the printout at the end is sort of the show method for the data structure. And so as you see, there's a couple of things there. There's a folder where basically the run method creates that folder and everything happens there. There is an ID, so it's all meant to make your workflows reproducible. So you can keep track of things. Here is the version of slightly more explicit, where you define with a keyword the model. So again, this is the function ClimateModels.jl provides random walker, which is a simple Julia function for random walk as a toy example. And this just defines the data structure. Then the full expanded sequence is this. We have 3 steps that are separate. One is setup, and the other one build, and the third one is launch. Technically, you don't always have to split up those 3 things, but it's typically how I think we achieve a lot of generality, because the setup is like choosing a configuration, preparing your folders and stuff like that to run. There's a build step, which, depending on the language, happens differently. Right? In Fortran, you do a make. In Julia, you let the thing compile for you. And then there's a launch method, which is like actually run the model and do your analysis. So in some cases, the build doesn't do anything. In some cases, it does more. But a lot of the handling of external languages can happen there, and that makes it kind of general. The setup method is the one that creates the folder structure for you. And so it does create a couple of things here. It creates this folder, and it puts a log subfolder in it, which is going to be Git enabled and keep track of everything you do with this workflow. The randomwalker.csv file here is the output from the launch command. So that's the model run output, basically. So that's all there is to it. Here is an example where we start using this more interactively in a sequence. So this has, again, the definition of the same model configuration, but now there's a parameter set with a file name and a number of timestamps. They are just provided as a name tuple. And then the run command is a shorthand for setup, build, and launch. It does all of it at once. The next set of lines is, what if now I want to do another run with 200 timestamps? So that's what you do. You change your parameter set, the file name. The put command basically reloads the function into a channel, which means that it's going to be executed next, and then you launch. The log command that I'm showing here is how you probe the history of the workflow. And so this is also how each one of those lines has been added to the Git repository, essentially. So as you see here, what we did in the top is all directly reflected in the bottom. So after the fact, you know what you've done, essentially. In this case, we started one model run, we then modified the parameters, and then we run again. So to continue on the theme of the power of text files, the fact is they are great for a few reasons, text files. One of them, we can read them as humans. And so that's one of the reasons that every model that deals with humans ultimately has their parameters in text files. You can have them coded in subroutines for the defaults. Typically, you provide some kind of name list or net text file to define what the model run looks like. Another thing that I love about text files is they're actually Git friendly. So you can actually keep track of what changes in them as opposed to notebooks. And they are standards. So the one I've chosen for ClimateModels.jl is TOML. So essentially, the way I deal with this variety of models is I have a way to get into memory their file formats. And then for that, I use TOML, and I read and write to that. So this leads to a notebook like this, for example, where you have exposed the internal parameters of this Hector model. You can click and change them, and then you rerun the model with another click. And that all gets stored into this custom parameters.toml file. Here is another thing I love about text file, and specifically I love Pluto notebooks. So Pluto notebooks, I'm sure a lot of you know, they are plain text files as opposed to what Jupyter notebooks look like. They don't have plots in them, and they do have all of the dependencies for the packages. So when you're using Julia, a one file, the Pluto notebook text file that you can read is all you need, because all of your dependencies are in there. And so that means that I can just use them with my framework immediately. So that's why I added another structure that makes every Pluto model, every Pluto notebook, a ClimateModels.jl ready to go model configuration. Looks something like this. Again, you just give the file name. In this case, the model is just the file name because it's a Pluto notebook. The name of the data structure has changed. It's Pluto config as opposed to model config, but everything else is the same. And I highlighted here that the build, in this case, does nothing. And so the setup takes your Pluto file and kind of deconstructs it, put it in a folder, lets you run it with the launch method after. Another thing that I've added, because I don't know if anybody else has this issue, one downside of Pluto notebooks is I keep updating their dependencies. Every time I change versions of Julia, and like if I wait 3 months, somehow they're out of whack. And so I created this little update function that now lets me just get the Pluto notebook, deconstruct it, update the dependencies, and rewrite me a notebook. So then I can launch it. So with this way, I can streamline all of my models that I'm maintaining in the form of, or distributing in the form of a Pluto notebook immediately and easily programmatically. So in summary, ClimateModels.jl provide a simple interface to models of all languages. If they're in Julia, that's even better. Interaction with models is enacted through text files, and I'm using TOML as a standard platform for that. The workflow steps are recorded automatically using Git, which makes going over a previous model experiment and understanding what's happened and starting a new one a lot easier in the future. So it supports reproducibility. I've given you a few examples of kind of established climate models that are available already, and I've explained how any Pluto notebook is readily ingested in this. So that's my summary, and I will just mention at the end, a lot of this stuff you'll find either through my GitHub repository directly, or I'm relying on packages that are distributed over those two organizations listed here, Julia Climate and JuliaOcean, where you can browse and find some of the packages I've mentioned. And that's it. Thank you for your attention, and I'll take questions if you have any.
I just want to kick off directly with a question that is like, we had a few talks now that basically more or less directly or indirectly complained about this like monolithic interface that a lot of the conventional models have, because it makes them less hackable, and you basically can only make the changes to the model as the developer who kind of thought about this is the monolithic interface, the name list, the config file, whatever you want to call it, that allow users to change. And so you can basically pass on anything that you can put into a text file. And you said that clearly that absolutely has an advantage when you like upload it to, like, let's say Git, it's a text file in the end, you have like everything in one place. But how does the interfacing now from ClimateModels.jl to, let's say MIT GCM with like name lists, compared to, let's say, if you were to do the same with Oceananigans, where suddenly you have to basically somehow interface to the entire, the script that basically then starts constructing the model, starts building the simulation and so on. How does that differ, and what is the implication then for ClimateModels.jl? Does that make sense?
Yeah, although I'm not sure I followed the whole question, but how does that differ? Not very much. I mean, the parameter set that I need to, when I want to change something in Oceananigans, I put in a text file, and that's it, right? Ultimately, when I look at Oceananigans, there's a lot of default parameters that are coded in text files, which are the GL files, right? So that's where you kind of find them. So you have to kind of hunt for them there or in the documentation. That's similar to any other model. It's the same in MIT GCM, really. The fact is that there is not a real explicit kind of text-based interface to defining your configurations in Oceananigans. So the only difference is I had to create my own. But otherwise, it's the same principle, right?
Okay. Okay. Yeah. And that one you just then upload to make it reproducible. Yeah. Okay. Any other questions? Questions? Oh. Yes.
Thanks, Gaël. Wondering about the use case here. So I imagine running some of these models could take a very long time. So you're envisioning, is the ClimateModels.jl in that use case where it takes a day or two to run a model? Or is that a case where you're just going to launch something in some other language and then log into Julia later on to evaluate things? I'm trying to think, how wide is the use case here for ClimateModels.jl?
I mean, all of the above. Ultimately, when you run something like MIT GCM or Oceananigans for a long run, right, you're going to put in batch mode and you send it somewhere, maybe on a compute node, right? That's what we do. That doesn't really have any impact on this, in a sense, right? You can, once you launch, that's why it's called launch, not run, in a way. It's like you can wait for the result to happen until it does complete, right? Some things are just computationally expensive. So that's one of the reasons. So I like the Pluto notebook. Maybe that's more useful as an answer. I like the Pluto notebooks for everything that's fast, right? Pluto notebooks, they're reactive, so they're going to recompute everything every time. So if you start your Pluto notebook and you have to wait for 3 days for the result to come back, that's not ideal, right? But they're great for a lot of other things. Now, that's one of the reasons have created this data structure to reuse them in that way, because this way you sort of streamline the thing and you separate out the steps and then you just launch and then you wait, as opposed to waiting in front of your screen. Is that right. Interesting? That's what I was thinking. Thank you.
Other questions for Gaël? No.
All right.
Okay, amazing. Then let's thank Gaël again.